So here we start. Good evening to all of you. We are back again with another exciting session. I, Ajay Jha, on behalf of ACS India team, welcome you to today's session. Just to update you on the upcoming ACS Science Talks in February, please feel free to visit the ACS in India webpage to register for these sessions. One can also find the past ACS Science Talk lecture recordings on the ACS India webpage. Feel free to scroll them and enjoy. To know more about the events Breakthrough Scientific Research, Product Launch at ACS, Chemistry News in India and Asia Pacific, feel free to subscribe this ACS India newsletter for free. We will provide the link into the chat box also. Now coming to today's session. Today we are pleased to have Professor Rahul Banerjee with us. Dr. Banerjee is currently Associate Professor at Department of Chemical Science, Indian Institute of Science Education and Research, Kolkata. He obtained his PhD from University of Hyderabad. Thereafter, he was a research associate at the University of California, Los Angeles, USA. Before joining IISER Kolkata, he also served as a scientist from 2008 to 2017 at CSIR National Chemical Laboratories, Pune. Professor Banerjee's research interest is in crystal engineering and metal organic frameworks. He has a long list of awards and accolades to his credit. To mention a few, the coveted Sati Swarup Bhatnagar Prize 2018 by CSIR, Swan Jayanti Fellowship by the Department of Science and Technology, CSIR Young Scientist Award, Young Associate of the Indian Academy of Sciences, NASI Young Scientist Platinum Jubilee Award, and many more. Professor Banerjee is a fellow of the Royal Society of Chemistry and currently serves as the associate editor of the Journal of the American Chemical Society. Before Professor Banerjee starts, few instructions for the audiences. Please post your questions into the Q&A section on the Zoom window and avoid putting questions into the chat box. In case of any internet issues, please stay with us. Now, I would like to invite Professor Banerjee to deliver his talk. Over to Professor Banerjee, please.
Thank you. Thank you very much, Mr. Ajay. So nice of you. Thank you so very much to ACS for this kind opportunity. I'm really happy and when I can see that in this platform I could give and share some of our recent work and discuss some thought-provoking questions as well. So without further delay, I would like to start, and I will make it a bit light because I understand that still we are not in fully back to the normal scenario. So as a result, we should. I wanted to make it a bit light. I don't want to make it too much with lots of equations and so on and so forth. So let's try to have a little bit fun here. Okay, so moving on, I have recently taken over and as associate editor of a Journal of the American Chemical Societies. We all know that. In case you need any assistance, any help, please do approach me in this email ID. These email IDs are already available in the website as well. And you can also send me email in my personal IISER Kolkata email ID as well. So I will try my best, at least give you some tips, at least if so that may come handy. Okay, so today, as you have seen in my slides, that I'm going to discuss something about morphology. So in the chemistry, morphology is not a chemistry term, and I didn't know that either, to be very honest. So when I was studying it, I found out these terms like morphology, phonology, syntax, these kind of terms are terms from linguistics. So morphology is the study of words. This is copied from Wikipedia. You can see it in any place. Morphology is the study of the words. It is basically the pretext, pretext of the grammar. So if you take words and think that words are the atoms, then what happens? Then you have sentences. So the sentences could be considered as molecules. Then paragraphs could be considered as large architectures, and the overall book could be considered as a material. So something like that. So we will look into it on that way, and I will go through it, even more in detail. Now, before I start, I want to show you a simple presentation and a simple slide. This is a slide on graphene oxide. We all know about graphene oxide. Many of us worked with graphene oxide. I have not worked with graphene oxide that much, maybe once or twice. But we all know that graphene oxides are 2D material. But take a look at this nice review article, and you will see that 2D material can be converted into multiple different types of materials. For example, like a 0-dimensional spherical. This is a 2-dimensional sheet, spray drying, and that gives you a 3-dimensional architecture. This is a 1D. So as you can see, a 2D material can eventually, on a macroscopic level, can be converted into a different features, different forms, different morphologies. So that's what the hallmark of today's lecture is. So I am going to discuss about porous materials. Okay, fair enough. So I'm going to discuss about porous materials. So what are porous materials? We all know porous materials. Porous materials, we use zeolites, porous carbon, porous polymers. These materials are all already there. We are wearing porous materials. Shirt, pant, all these things are made of porous materials. So what should be the feature of any material for sale? If it has to come to the market, it has to be, first of all, inexpensive. It has to be cheap. Otherwise, who will buy it? If your shirt would have been, let's say, 1 crore rupees, we would have all be roaming around without shirt or any clothes, right? So porous materials. Now, second is, in the material that I am talking about, it is not necessarily for all the porous materials. Then I expect it to be crystalline. Then I expect also it to be porous and chemically stable, because if it is not chemically stable, then it will degrade very quickly, and your hard-earned money will disappear. And when I'm making it in the industry, I should be able to make it quickly, so that I can I can send it to all over the world, and I can make it readily available. And flexible materials should be there. It should be flexible. It should be modifiable. Okay. Now, the material that we are talking and we are working right now is based on a very simple concept, very, very simple concept. These are called covalent organic frameworks. Why? Because if you take a simple organic building unit and react with another organic building unit, one is C2 symmetry, another is C3 symmetry, then you eventually create this nice, hexagonal architecture. These hexagonal architectures, they will assemble one after another, and then they eventually create this nice porous structure which precipitates out from the solution. So why it is covalent organic framework? Because it is, after all, made by covalent bond. They are organic in nature, and they together they have made a framework. So covalent organic framework, very simple nomenclature. So these materials are crystalline. As I said to you, these materials are crystalline in nature. So like this, as you can see, there are many different ways you can make these materials. I will show you the crystalline properties in a minute. So you could change from C3, C2 combination, you can have C4, C2 combination, and each time you change the organic link, you get a different porous material. So that's the beauty of it. So you can see how easy and how quick you can make it. These are nicely structured, as you can see, these are nicely structured. This was invented by Omori in 2006. So then, when we started doing the work, we of course, I didn't invent it. So we were thinking what to do with it. What are you going to really do about these materials? So we figured out that the porous materials are made by a few different reactions. For example, this is the boronic acid trimerization. Another is the SIP-based condensation and boronate ester. Every cases you can see this water goes out of the system. So once you take out the water, following the Le Chatelier's principle, the reaction moves. That is the simple way of doing it. So, all right, and then when we started the work, when we figured out that we really need this reversible reaction. Why? Because if you do have a reversible reaction, you can organize things, break it, organize, break. For example, if I give you a bunch of chairs and ask you to organize it, so first you will put them, then you will assemble them, move them a little bit, make them in nice rows and columns, and then you will have a nice stack of chairs. right? If you could have just do it once, and then this would have been completely haphazard. So keeping that in perspective, we figured out that these covalent organic framework materials are quite unstable. Why? Because this is a reversible reaction. A reversible reaction can go in forward direction. It can also come back in the backward direction. So with these materials, in presence of little bit of water, they hydrolyze. So this is the big problem we figured out. All right. We found out that, okay, that is a problem. Second problem is, despite this is a huge interest among the researchers, you can just type in Google covalent organic framework and you'll see papers after papers and review articles after review articles all over the world. Despite all this interest, the problem with these materials were that you are unable to make it in a bulk scale. Why? Because you want these materials to assemble, or the building blocks to assemble and stack them, and they get stacked up, but they are not school children, they are molecules. So when you will mix them and try to make this material, something else will happen. What will happen? They will react very random manner and eventually just precipitate like an amorphous polymer, which will be totally good for nothing. So what to do about it? That's a big problem. So the way we started, and previously, once again, as I said, Professor Omar Yagi, he has invented this compound. So when he, they pulled it, or many of us, we need to cut down these, we need to have this thermodynamic product and this kinetic product we don't want. So what we do is we use something called freeze, pump, thaw. I mean, those who knows about the freeze, pump, thaw knows how brute this technique is. So this technique, you have to first fill in everything, then it has to, you have to do a freeze drying, then seal it, then put it inside the oven at such a high temperature, 120 degrees centigrade temperature, unbelievable. For 3 days, then you break it, and then only you get this tiny, teeny compound, and then you call it like, okay, I made the compound. This looks, so this is okay for some small scale, laboratory research, but never worthy for industry. So we figured out that there are few issues. Issue number one, first, we can't make COFs in gram scale. It was still stuck in milligram scale. They are not chemically stable. We thought, okay, that could be an interesting research objective. So we started. And we figured out that it is not us who has thought about it as well. I mean, we are not alone in this setup. People have already figured out that if you take the covalent organic framework, add a little bit water, that is completely degraded, completely gone, hydrolyzed, completely gone. Okay. So what we thought that, okay, all right. So we take up this covalent organic framework, and we take the same building blocks and we make the covalent organic framework. Okay. But we need the reversible reaction to get the crystallinity. And when we have a reversible reaction, we do not get a stable product. So what to do about it? So what we did, first we did with same amine and aldehyde based system, and we made a reversible reaction and formed this product. We deliberately placed these hydroxide functionalities over here so that this process is not stopped here. So once this bond formation happens, then what happens is that these hydroxy functionalities, they tautomerize. Look at this. This is the bond. So previously what we had is this C double bond N, which is very nicely hydrolyzable in acid, base, and so on. But now what you have? Now because of the tautomerization, you did get this nice tautomeric structure, and where it loses the aromaticity and get the tautomeric structure. And here now you can see C double bond O, C double bond C, C single bond N, C single bond C. None of these are hydrolyzable in base and acid. Okay. Of course, if you add aqua regia or very concentrated sulfuric acid, these will go bad, of course. But beyond that, hydrochloric acid, sodium hydroxide should be okay. This concept was already known that if you take a salicylaldehyde and react with aniline, you will get only the enol product. But if you take a fluoroglucinol trialdehyde and the aniline, you will get the keto product. This is already available in Cambridge structural database. You may kindly take a look at it, and you will see from the bond distances that this is a keto product, not enol. Okay. So we just took this idea, put it into the extended structure, and voila. What we got is the following. You can see this is the product that we have made. This is the powder diffraction data. I apologize for a weak and not so good quality powder diffraction data. I will show you some better quality ones very soon. And you can see before and after treatment in boiling water, acids, all the surface area and everything is absolutely fine. No problem. So that is something really interesting. And we figured out, all right, this worked out fairly well. And we did reacted with sodium hydroxide as well. The pristine one didn't remain stable for a longer period of time. But if you methylated it, and it remains fairly stable in sodium hydroxide as well. So that tells me that, that we can now work with this material, and now we could make a material which is crystalline, which is porous, and which is chemically stable as well. However, what about the quick synthesis? What about flexible materials? What about all these things? Okay, let's come back to that one by one. So before that, what I wanted to look into is that, in metal organic framework, or let's say in any solids, especially the crystalline solids like zeolites and other materials that we use, there is a direct correlation between the morphology. So this is the morphology I'm talking about. That morphology we discussed, the morph, the polymorphs, different type of morphs or phases. So this is the morphology I'm talking about. So this morphology, or these morphologies, are pretty well connected with their crystal structure. Very well connected. So that's why you can actually pre-think or pre-design a material and get a final product sorted. Whereas for covalent organic frameworks, there is no correlation whatsoever. So there are so many different types of morphology for the same hexagonal or the tetragonal structure. Same thing, absolutely same. Same material, and you crystallize it in different way, and you get different morphologies. For example, like this case. In this particular case, as you can see, for the same material picked up different morphologies. Similarly, in covalent organic framework also, we could get completely different morphologies of, right now I dare say that as per our wish. For example, this is the same 2D material like the graphene oxide, and you could now make fibers, spheres, nanosheets, films, foam, and so on and so forth. So you could actually diversify the same 2D material like you could do for the graphene oxide, the same thing. However, please note that you have a lot of opportunity here. You have carbon nitrogen bonds, carbon oxygen, and you have a functionalizable scaffold or functionalizable domain to take it to the next step. So this is an opportunity that I would like to envisage and discuss today. Not only that, you can also interconvert these morphologies one to another. For example, these spheres can go to the film, and the film can go to the foam, and so on and so forth. That part I will skip. I will not have that much time. Coming back to the original question. Okay. So these covalent organic frameworks, like as I have told you, take a look at it. This is also hexagonal. This is also hexagonal. This gives some rod-like morphology. This gives us very sphere-like morphology. Why is that? There is no correlation. Question comes, why is that? Always we used to think, why is that? So we thought that, okay, let's dig deep. Let's dig deep. Let's not just keep on asking this question to each other. There is no point. So let's dig deep. So we took a simple organic molecule, and reacted with an aldehyde. Same, this is a ship-based reaction, and there is no ketoenol tautomerism, as you can see. However, these materials are also fairly chemically stable because of this intramolecular hydrogen bonding. So these nitrogens are now engaged into this intramolecular hydrogen bonding, and that gives it sufficient amount of stability. Now you can see the PXRD patterns are improving. The surface area we reached almost 2000 meters square per gram. We have gone even higher than that. But the important part that what we have understood during this process is these materials, why are they taking this weird hollow sphere-like morphology? Why they are so hollow sphere, and what is there in the hollow, and can we use it really? These kind of questions that popped up. So we thought that, okay, all right, these are hollow spheres, fair enough. Let's find out and let's try to understand why on earth they are hollow sphere. What is the point? And second question is, why should we really bother about it, at the end of the day? So what we did is we studied the literature a little bit carefully, and Wilhelm Ostwald, has already said many years ago, more than 100 years ago, that if you have smaller crystallites, they will sacrifice themselves so that the bigger crystallites even grow bigger and larger and larger and larger. So he has already said that long ago. Okay, so he's got the Nobel Prize in Chemistry in 1909 for his beautiful Ostwald ripening concept. So similarly, we found out that in this case also, if you have this type of polymeric structure, two-dimensional polymeric structure, they are crystalline in nature. They do have a very nice intramolecular hydrogen bonding. But so we used to do the reaction for 72 hours. Okay, fine. We decided that let's stop the reaction. We stopped it at 12 hours. The spheres are all gone. They have not even formed. We then isolated the product, purified it, and checked their surface area and figured out that their surface area is exactly identical like this. So it has crystallized to these smaller, tiny particles like this. So initially there was a reaction, then the stacking, and you get these tiny particles, these small, tiny particles, which just floating randomly, not even formed any sphere or for say any structure whatsoever. So we studied, and you can see these hexagonal pores so nicely visible in this routine TEM, or in a routine TEM analysis. Okay. Now, what happens with time is these particles slowly start assembling, and as you can see now, these particles, as time goes on, this is 36 hours, time goes on, these particles start assembling. If you continue with the reaction, and eventually form these field spheres like this, where all the materials are crystallized still inside, slowly dissolve and go to the outer periphery, and then recrystallize there and give you a much more tighter, hollow spherical architecture. Absolutely tighter. And the porosity and the crystallinity that you are seeing, that is coming not because of the pore here, it is coming because of this, the wall. So whatever you have inside, or whatever the space you have inside, is completely unutilized, I would rather say. So this is the phenomena. So you have these nice hexagonal crystalline stackings. They form these nice particles. These particles assemble and eventually form this hollow sphere structure. We even loaded some enzymes just to check whether it is getting loaded or not. And we figured out that we wanted to load it here inside the hollow architecture. Everything got absorbed only on the surface. It is such a porous surface that we can see. So that is very interesting. And we also found out another interesting feature is that these materials, when you leave it as it is, if you leave it as it is, these materials will assemble and eventually form this nice, gigantic structure with lots of spheres assembled with it. So this is very important, and that gave us more insight that we could actually probably take these spheres and go to the next step. What is the next step? The next step was, once again, very simple. You take the linkers, aldehyde and amine, put it into DCM, just reflux for some time. Then after the refluxing, you just put a bilayer, water and DCM bilayer. These spheres that we are talking about nicely start assembling and forms films. So you can see how beautiful they are. When they are spheres, they had a powder diffraction, everything. This just starts assembling. How? The way it happens is I will skip these powder diffraction and busy slides. I'll just come to the point that you had these spheres. It just gets converted into the films. Look at this. I was really stunned to see that. Look at the nice, thick, and uniform and smooth films. And you can even see some of these spheres on the corner if you look at it a little bit carefully. Okay. So how it happens? The happening process is very simple. So initially you have nice discrete particles where you have the amine and aldehyde on the surface. These particles like this, amine and aldehyde on the surface, these particles, initially they were separated with each other. But with time, when you give water and DCM bilayer, these particles will start reacting at the interface, exactly like this, like at the interface, and eventually form a nice film for you. With particle size analyzer, we could find out that the particle size changes with time, and it becomes much more lumpier or much more, and after some time we couldn't really measure it. So this is a very important and interesting feature that we found out, that where you could take these spheres and connect them or assemble them into a nice film of your choice. That was very, very interesting. We could coat it on a hollow fiber membrane, but let us keep that for now. Second point, what if we want to make it in bulk? If we want to make it, we don't want to get into this through this hollow sphere route or field sphere route. Okay, fair enough. You take the aldehyde at the bottom layer, this dichloromethane. You add a little bit of water, pure water, deionized water, and then add a solution of this amine and this amine solution on top of it, so that they can interact at the interface. At the interface, they will interact and they will form very nice thin films. If you wish to make it a thin one, you can do it. Now, question is, why we want to all on a sudden make it in the bulk quantity, these thin films? I recently visited Tata Steel, and I found out that these are the places they took me, and this is the blast furnace where all this coal is going, and the CO2 and all these things, whatever the gases are coming out, they are coming out through these pipes. A lot of people ask, what does these metal organic or covalent organic frameworks are good for? So we all say they are good for CO2 capture and this, that, whatnot. But think about it, CO2 is coming through this. And if I am making this sphere to film and whatnot, eventually, I will be keep on making film throughout my life. This pipe will never fill. So you need to figure out a way to make it in the bulk. So that's when we thought that let's use a simple polymerization technique, or take a help of this polymerization technique, that is the interfacial crystallization or interfacial polymerization, and make these thin films into bulk. So coming back, what we did, very simply, we took the simple aldehyde, added some water on top of it, and after that added the amine, slowly let the aldehyde and amine react. And because it's a ship-based condensation, the reaction is reversible. You will get eventually, at the first step, you will eventually get this nice, as you can see, these thin films. You can get it. These thin films, I'm so proud to say, you can vary the pore size of the film. Number one. Not only that, these films are microporous by themselves. Just the film, these film pieces. So these are microporous by themselves. And the important part is, if you take this film and you check that, you can see this is how uniform these films are. Of course, there are little bit of deposition. I won't say no to it. There are little bit of deposition, but overall, you could make a different size. You could make 100 nanometer film. You could make 1 micron film. You could make 120 micron film also. That is totally up to you. We found out a little bit more detail about the synthesis, and this synthesis part, I will just show it to you. So what happens initially in the aqueous layer or the interface, this aldehyde and amine forms small oligomeric particles. These oligomeric particles will slowly assemble into this nice thin film-like architecture. So this oligomeric covalent organic framework will eventually form this nice polymer, and eventually you will start seeing the powder diffraction pattern popping up after few days, let's say after 2 days or so. These, as I said, you can make thick films. These are 2.1 micron. You can make 120 micron. You can go up to that level. And as you go thicker and thicker, of course, the roughness increases, because there are lots of assemblies now. And this is not just one layer coming on top of each other. There are lots of assemblies. So you could do that, and you could use these to separate different dye molecules exactly like a filter paper. Exactly like a filter paper, but please keep it in mind that you have to use the films. You cannot use powders. You cannot use the powders and do a pellet pressing and make a pellet and prepare a thick pellet out of it and expect that it will do the same job. It won't. So you can do a nice molecular sieving using these films, and these molecular sievings are very much in like other membrane-based sieving that you could do. Of course, needless to say, please make a note that these materials are still porous materials, so there will be some seepage and some adsorption as well. But overall, this is still a very much a membrane separation, but you need to make the film. You cannot just use a pellet and expect that will do the same job like that. You have to keep it in mind. So you have to grow the film, and it has to be continuous. There cannot be breakages in the film. So these are the filter papers that we commercially use. This is a cellulose filter paper. We also use syringe filter. And what about the nanometer size filter paper? So this is what now I am about to show you. So what we did is we took these films. They are not exactly aligned on the nanometer level. Please make a note. This is just for the representation purpose. This is a small fragment of this. Okay, this is a small. So not that this particular layer will be in this way. So these, what about this nanometer level? Since we have these nano channels, so what we did is we took the same aldehyde and amine, and we made a 120 micron thick film, as you can see, thick film, and these are very thick film. Not every part is exactly aligned. Once again, I repeat, but some part at some zone will be perfectly aligned with that level, and that will give you the filtration. The filtration that will come. So what we did, we just took the simple nanoparticles, which are commercially available. These are thiol-based nanoparticles, 2 nanometer, 4 nanometer, 10 nanometer. Run through it. So this is the cross section of the film that I want to show you, and you can see there are lots and lots of defects. So these nanoparticles will flow through it. These are very, very large defects, but at some point they will get stuck, and there is an alignment or orientation which let these to come through. And then, as you can see, before filtration and after filtration, you can see that the filtration, initially it was a completely haphazard, and after the filtration, you can see that particles which are only of around 2 nanometer size that came out of the pore. So this is what has happened during the process, and we did it, and you can do a back flashing, and during the back flashing we found out that there is a little bit of adsorption on the other side of it, and if you back flash, you can reuse the film for some time. Okay, now I'll finish it. I'm running out of time. So if you want to make a thicker membrane, if you want to make a heavier and a larger one, what you could do is you could do the same thing, just mix aldehyde and amine into one pot, make a slurry, and then add it into a knife caster, and just do a knife casting with a little bit of heat, and you should be able to make a much more thicker coupons out of it. So what we did is we just took these coupons once again, and we checked their organization. You can see these layers are organized, and that is what I'm trying to tell you. Through these, all the particles will come out. But over here, you can see only a few, only the size selectivity that will happen. These thicker films are even porous also, like the thin films. Their porosity is very much comparable. You can see this thick film about 1,000 meters square per gram porous. So which is really stunning, because generally the thin films or thick films, they're not up to that porous, because you can see the organization of the porosity is completely broken. We could do a size selective, once again, a separation, and you can see over here in molecular weight, this is the PEG, which does not should not have any molecular cutoff, but we could still see a nice cutoff of the PEG molecules as well. So we did, as I said, we did a bunch of separations using these materials. Separation also comes with some small amount of adsorption at the surface or at one contact level, because at the end of the day, these are porous materials. But eventually, we could separate all these solutions fairly easily. And we are now trying to go to a higher concentration and see how that works out. As I said, I request you, and I repeat, that if you make just pellets, not the films, then obviously you will have this kind of fragmentation. And that kind of separation will be only based on absorption, not the thin film. So you have to make the film, and before you get into such kind of separations, that I would request or urge you to look into. So I guess I could give all of you more or less sort of an idea that, you know, how from one morphology you could go to another morphology and so on. Also, you can see the fibers has gone to the spheres, and spheres has gone to the films and other things. So I could look into that, and I could hopefully I could give you some of these aspects or some of these ideas that probably give you some kind of visibility and as well as the interest into this particular field. I will finish off my presentation with a small work that I want to show you. So these are the different varieties that you could see so far, which I have already gone through it. So I will show you another variety that I want to share with all of you. Let me quickly go to that particular slide, and so that I can show it to you. Yeah, so this one. So this is another interesting work that I've done, and that is where I'm going to finish it. So these are the covalent organic frameworks that you have seen so far, nicely stacked up one after another. What if we could break the stack? Think on this particular way. You have stacked papers. We put it for a printer. In our printer, we take the stack of papers we purchase from the market, we put it. Each paper comes out with a print. We take the same stack. Suppose if I could give some defects into that stack, I could pull up some part of those papers. So overall, you will still have a stack, still have a porosity, but eventually inside the structure there will be lots and lots of defects. Okay, and then these kind of defected materials like this, you can see this is the material where the walls are very much porous, but internally there are lots and lots of voids and defects. And these defected materials, when we just put it into any kind of pollutant, now we are trying to work with arsenic, as you know, in this region, West Bengal and Southeast Asia and these places, arsenic is a key issue. And you don't get any idea that you have consumed arsenic until unless it about couple of years, 2-3 years pass. Then you will see your hand, face, all these places. There are a lot of really horrifying pictures in Google. You will see your face and all these places. This arsenic pollution will create this poisoning, and eventually that will be a painful death. So what we are trying to see, if these materials can absorb arsenic, and that is a very tiny quantity, so that is our target. We did with some of the dyes, regular dye that we have used in our laboratory. And we found out that this can also go to some of these iodine, KMNO4, other dyes as well, and it can do a very quick removal. You can see almost like instant, in a 0 second, almost like an instant. It will take it up, maybe over 10 seconds, 20 seconds, based on the foam material. Very simple concept. So you have a foam type of material. So this you can see, these are the porous things we are talking about. So in this material, these are the porous things, and you can see lots of black voids, which there is nothing. These are the cross-sectional tomography images, which shows the lots of voids, which will be so much effective for the fast diffusion of the pollutants. Otherwise, you could just use porous carbon or other things like we use in a regular filter. We took it to the one step further. We are working with the 3D printed material. You can make these materials in 3D printed as well. And we make this 3D printed chunk of bricks, small bricks. In our laboratory, we are trying to work and see whether we could use these for the CO2 to value added product formation. So I believe that I gave you an overview of the work that we have been doing. We have summarized everything in this review article. So if you are interested, you are welcome to take a look at it. If I can be of any help, if I can clear some of the doubts, I'll be more than happy to do so. I moved to ISAR Kolkata only a couple of years ago, and this is my group now. I sincerely thank all my students. Kaushik and Himadri, they moved from MCL with me, and both have finished their, Kaushik has submitted his thesis, Himadri will submit in 10-15 days or so. My colleagues Thomas Heine, Matthew Edicott, and also Dr. Kharul and Robi Broto from IIT, deeply acknowledged. They have been working with me for quite some time. We have been doing some collaboration with MCL, with Dr. T. Ajit Kumar now. Finally, I must thank my CSIR, who has been very generous to fund my research. I am not in CSIR family now, but I was there for almost 10 years. DST has been very kind to me. Now CRB, very kind to me. They have been supported my research, and I'm indeed thankful to them. ISAR Kolkata and of course NCL. These were two host places where I worked. So I mean, ISAR Kolkata I'm working, NCL I worked. So I am deeply thankful to them. Finally, as I said to you, that if you have any questions regarding the work, I will be more than happy to answer. If you have any questions regarding the Journal of American Chemical Society, maybe after this presentation we could take it up maybe at some point based on our mutual time. So I thank you all, and I thank you very much once again for attending this meeting. I hope it was not too boring, and if it is, I sincerely apologize for that. Thank you very much.